there. Welcome to Lesson 2 of Plastic Ingenuity's course on sustainable packaging. My name is Sarah Weber, and I am a sustainable packaging engineer at Plastic Ingenuity. This lesson will be focusing on life cycle assessments, also known as LCAs, and how they can influence sustainable packaging development. A life cycle assessment is defined as the systematic analysis of the potential environmental impacts of a product or service during the entire life cycle. Benefits of utilizing life cycle assessments for sustainable packaging development include quantifying key environmental impacts such as GWP, water usage, fossil fuel usage, energy consumption, and freshwater eutrophication. Exploring and comparing design choices, material selection, manufacturing processes, and more. Identifying hotspots for improvement by evaluating the stages that have the greatest environmental impact, and leveraging data-driven results to make sustainable design decisions with key stakeholders. But before we jump into life cycle assessments, let's do a little background research on carbon emissions. Greenhouse gases include carbon dioxide, methane, nitrous oxide, and fluorinated gases. These gases contribute to the greenhouse gas effect, a process where heat is trapped near the Earth's atmosphere, causing an increase in the Earth's temperature. This effect is essential for maintaining the habitable temperature of our planet. However, an excess of certain greenhouse gases from activities such as burning fossil fuels and deforestation has led to disrupted weather patterns, higher global temperature averages, changes in rainfall, and rising sea levels. These are the effects of climate change and will likely present challenges to our society and environment in the future. According to the EPA, carbon dioxide is recognized as the predominant anthropogenic greenhouse gas as it presently contributes to the majority of warming associated with human activities. Therefore, carbon emissions are prioritized when accounting for and reducing greenhouse gas emissions within organizations. Like financial accounting that tracks income and expenses, carbon accounting operates similarly, where a carbon inventory represents an organization's emissions. Carbon accounting categorizes CO2 emissions into 3 groups: Scope 1, Scope 2, and Scope 3. In concordance with the Greenhouse Gas Protocol, the EPA defines Scope 1 emissions as direct emissions that result from sources owned or controlled by the organization, such as fuel combustion of generators, furnaces, or vehicles. Scope 2 emissions are indirect emissions from purchased electricity, heating, or cooling. Scope 3 emissions, commonly defined as value chain emissions, encompass a broader range of indirect emissions, such as purchased goods and services, upstream and downstream transportation and distribution, employee commuting, business travel, and end-of-life treatment of sold products. A carbon accounting process systematically tracks, calculates, and reports our emissions within a given year. Starting with data collection, a company will gather data related to their emissions, including energy consumption, manufacturing processes, and supply chain activities from all the sites within the calendar year. Once the data is collected, the emissions are calculated using emission factors, which relate to the quantity of pollutants associated with an activity. The outputs of these calculations are communicated through the unit of carbon dioxide equivalents, or CO2e. This is the standard unit for measuring carbon emissions. This is one of the key metrics of a life cycle assessment. As previously stated, a life cycle assessment is defined as the systematic analysis of the potential environmental impacts of products or services during their entire life cycle. This includes, but is not limited to, the environmental impacts associated with raw material extraction, manufacturing and assembly, transportation and distribution upstream and downstream, and end of life. The inputs of an LCA are the materials used and the weight of those materials, manufacturing and assembly processes used, transportation modalities for upstream and downstream distribution, such as truck, airplane, or ocean freight, distance traveled by a certain transportation modality, and end of life. The end of life impact calculation incorporates the most likely fate of the product or package, as its components are based on typical curbside municipal waste management. These are certain percentages for recycling, incineration, and landfill based on the region. Once these metrics are entered as inputs into the LCA, the outputs are often GWP, global warming potential, which is usually measured in kilograms of CO2 equivalents, fossil fuel usage, water consumption, freshwater eutrophication, cumulative energy demand, mineral resource usage, freshwater ecotoxicity, or human impact. Now that we've defined the key environmental impacts, let's discuss how we can use an LCA to compare and explore material and design choices for packaging while identifying hotspots in need of improvement. In this example, we will be evaluating the environmental impacts of down-gauging a PET thermoform and incorporating recycled content. When we evaluate the results, we see the thermoform with the higher gauge and no recycled content has the highest global warming potential, fossil fuel usage, and water usage. We see that the material is by far the main contributor to the environmental impact. The easiest way to lower emissions from the material is by incorporating recycled content. By transitioning to 100% post-consumer recycled content, we can decrease the GWP by 43%, decrease the fossil fuel usage by 65%, and decrease the water usage by 77%. But wait, there's more. This packaging designer wanted to go above and beyond to minimize the material usage by down-gauging by 5 mil. This decreased the GWP by another 9%, fossil fuel by 5%, and water by 4%. This is the power of an LCA when needing to compare sustainable packaging options. This method allows for sustainable decisions to be made with data-driven approach, making it easy for packaging professionals to report environmental reductions to align with overarching corporate sustainability goals. Although this was a rather simple example, the impact of utilizing an LCA is apparent. Life cycle assessments are indispensable for sustainable packaging development due to its comprehensive evaluation of environmental impacts across the entire life cycle of packaging products. By assessing factors such as resource consumption, energy usage, emissions, waste generation from raw material extraction to end-of-life disposal, LCA provides crucial insights. These insights guide designers and manufacturers in making informed decisions to minimize environmental footprints and enhance resource efficiency. Ultimately, LCA enables the development of reducing environmental burdens, advancing towards a more sustainable future for packaging. Stay tuned for the next lesson on sustainable materials.